19th lecture, 3rd February 1995. We continue our discussions on double tuned circuits. In particular, we consider a couple of examples and then we shall have a general discussion on double tuned circuits. We had started the general discussion the previous day. That means transfer functions of the type that is obtained with double tuned circuits can also be obtained otherwise. And one of the examples I gave was electrostatic coupling through a capacitor. It could also be a resistive coupling. It could also be some other kind of coupling which we shall discuss at the end of this class. Now, the example that we had taken was a transfer function which was given as a s cubed divided by s plus 2 plus j 100, s plus 2 minus j 100, then s plus 2 plus j 106 multiplied by s plus 2 minus j 106. This was the transfer function, and we wanted to find out the frequencies of maxima omega 1m, omega 2m, where does the transfer function attain a maximum value. We wanted to find out the bandwidth. For bandwidth we have to find out omega c2 and omega c1, then zeta, k the coefficient of coupling, the constant A, and the maximum value of the response. These are the things to be found out. And if we look at the the pole 0 diagram, if we look at the pole 0 diagram, there are 3 zeros at the origin as in the tuned circuit, 3 zeros at the origin, and if we exaggerate a little and distort the scale a little, there are poles here and here, there are poles here and here, where this distance is minus 2, this is 100, all right, and this is 106. This is minus 106 minus 100. Of course, they will have to be multiplied by j. Pardon me? Thank you. That's correct. 100 would be up and 106 would be down. Now, obviously, omega n, well, the poles, the distance from the origin along the vertical axis is much larger than the distance from the, I beg your pardon, the distance from the vertical axis, that is this distance, is much smaller as compared to the distance from the horizontal axis, and therefore zeta would be a small quantity. We also assume that the coefficient of coupling is sufficiently small, which is suggested by the symmetry of, well, the closeness of these two poles, okay, and therefore our omega n, if you recall, this would be j omega n, midway between the two. So omega n is 103. That's obvious. If we want to find out the two frequencies of maxima, we will have to draw the picking circle. Now, the picking circle has been drawn here. The green circle here is the picking circle. Let me explain. This is the sigma axis, this is the j omega axis, and the intersection is now at omega n, and the two poles, that is, what we are doing is we are zooming on this part, okay, and this is omega n, this is 106, this is 100, okay, you understand why? These are the two poles. We are zooming on the two poles on the upper half of the S plane. 100 and 106, and this is omega n 103. So, the poles are here. This is this point is -2, this point is -2, and the peaking circle is drawn with -2, this point as the center, and the distance from this point to the pole as the radius. So, this is the green circle which cuts the j omega axis at 2 points, omega 2 max and omega 1 max, and if you notice the omega 2 max, all right, omega 2 m minus omega n whole squared, that is, consider this right angle triangle, this squared plus base squared, base is 2 and therefore plus 4 would be equal to the hypotenuse squared, which is equal to 3, therefore it is 9. Therefore, omega 2 m minus omega n is equal to 5, therefore omega 2 m is equal to, I beg your pardon, root 5, that is 9 minus 4. Okay. Well, therefore omega 2 m is equal to omega n plus root 5, that is equal to 103 plus root 5 is 2.236. So, this is 105.236. Omega 1 m can be obtained by inspection. It is to be symmetrical, number 1. Number 2, if you take this as minus root 5, I think the answer is obvious. Okay? And therefore, this would be 103 minus 2.236. So, this would be 100.764. Okay? These are the two frequencies of maxima. Now, we go back to the to the peaking circle. We have found out omega 1 and omega 2. Then we look for the bandwidth. For the bandwidth, you see the peaking circle intersects at 2 points, omega 2 and omega 1, and it intersects the sigma axis at this point, whose coordinate obviously is 1, because the radius is 3, this is 2, so this is 1. Now, from this point as the center and the distance from this point to the pole as the radius, you draw the peaking circle, which is the orange circle. It cuts at 2 points, omega C2 and omega C1, and what we have to find out is omega C2, and if we find omega C2 by symmetry, omega C1 shall also be found. You notice that omega C2, if I draw this, let me use a light color. Okay. If I draw this line, then this right angle triangle, this line is equal to, what is the length of this line? 3 root 2. Okay, because this is it is the same as this. This is 3 and this is 3. So, this is 3 root 2. 3 root 2 squared would be equal to omega C2 minus omega n whole squared plus 1 squared. Therefore, what I get is the following: omega C2 minus omega n whole squared would be equal to 3 root 2 squared minus 1, and therefore omega C2 is equal to omega n plus square root of how much is this? 18 minus 17. Okay. So, this is equal to omega n plus square root of 17 is 4.123. All right. Therefore, omega C1 by symmetry would be omega n minus the same quantity. Therefore, the bandwidth is the difference between the two. It would be 8.246. You must put the appropriate unit. What is the unit for bandwidth? Frequency, radians per second. Okay, radians per second. We don't have to absolutely find out what is omega C2 and omega C1, because we only want the bandwidth, but we had to determine this. Next, yeah.
So, when you are saying about the bandwidth, we need not find the center point of that between two points. That how much is the depth?
Very interesting question. Yes.
So that will be just h omega naught.
That is correct. You will have to find that out. You see, All they are asking is the bandwidth. Now bandwidth will not have a meaning if this is the situation, for example. If the dips below 3 dB, it will not be useful. In this case, you shall have to check. I didn't check this.
First you have to write that h omega naught is less than root 2 of that.
That's right. So you have to find out h of omega n magnitude and see whether it is less than 1 by root 2 times this or not. If it is not, then this bandwidth is meaningful. Okay? Good question. The other things that you have to find out are the well, we can find out zeta omega n is equal to 2. It's given. Zeta omega n is the distance of the pole from the vertical axis, from the j omega axis. Zeta omega n is 2, therefore zeta is equal to 2 by omega n, which is equal to, we need the value of zeta to be able to find out the value of the constant A, capital A sq. Okay. So 2 by omega n is 2 by 103 and this is 0.0194. We also need the value of k. K is specifically asked for and we know omega n k by 2. Omega n k by 2 should be this distance 3. Okay. This is equal to 3, therefore k equal to 6 divided by 103 and this is 0.0582, which indeed is much less than 1. This is also much less than 1 by 50. Okay. So zeta squared would be much farther less than unity. Okay. Finally, you find capital A is twice zeta omega n k divided by 1 minus k squared. You substitute all the values, then you get 0.2328 and the maximum value of the transfer function h max 1 by 2 1 minus k squared, that is equal to 0.5009. Finally, did we find out an expression for h of omega n? Did we do that earlier? H of omega n? Did we or did we not? We did find out the ratio in one of the examples yesterday. We did find out the ratio of m omega max to m omega n, didn't we? What was the expression?
1 by sin theta.
And what was the value? K by 4 zeta plus zeta by k. Okay, now let's check this. Alright, compared to the maximum, or we take the other way round, that is m omega n divided by m omega max. It's now easy to find out what is the ratio. If this ratio is greater than 1 by root 2, greater than or equal to 1 by root 2, is the point clear? Yes or no? Then the bandwidth that we have found out has meaning, otherwise it does not. So this expression must be kept handy also. Alright, this is how you check whether the bandwidth that you have found out is meaningful or not. Let us take another example. Is there any question on this?
Suppose in case of 3 poles, 3 zeros.
In the case of 3 zeros, yes.
In this case,
Yeah.
if there was not 3 zeros, suppose 1 0 or 2 0, so then there won't be any change.
Alright, we will take that case now. We will take an example with 2 zeros. Okay. We take this example, h of s is equal to a s squared divided by, this is given, s plus 4 plus j 50, s plus 4 minus j 50 multiplied by s plus 4 plus j 60 multiplied by s plus 4 minus j 60. This is what is given. We have to find out the frequencies of maxima, omega max. If there are 2, both of them, 1, 2. You have to find out omega C1, omega C2. This will always exist, whatever the value of k and zeta, because it is a band pass. Is it a band pass response now? You must be careful. There is a power of 2 here. It is band pass because at the origin, at s equal to 0 it is 0, s equal to infinity is also 0. So in between there must be a maximum, and therefore there must occur an omega C1 as well as omega C2. You have to find out the value of q. You remember q is 1 by 2 zeta. Okay. Then the value of a and the value of the coupling coefficient k. These are the things to be found out. The first observation that you make is, because the power is s, the power of s is 2 s squared, obviously if it is a double tuned circuit, the output has not been taken across the resistor. If it was taken across the resistor, the power would have been 3. So one power has been reduced. What does it mean? Capacitance. So the output has been taken across the capacitance, which means that the value of A here would be related to the value of A, the previous value of A, which you shall denote by if the output is taken across R. How will these two be related? If you recall, the output is I2 multiplied by R in the previous case, and in this case it is I2 divided by SC. This S makes the power of S 2 here, and the constant, therefore the constant would be, I have to divide by R and divide by C. There is a C in the denominator here. Alright, I2 by SC, which means that I have to divide by R, divide by C and divide by S. Divide by S, that takes care of S squared. That is how we find out the new A. We don't have to derive the whole double tuned circuit again. We can do it by inspection. The only difference is that the output has been taken across the capacitor.
And the same thing we done in the single tube circuit.
Pardon me? Yes, yes, of course. Of course. All known results can be utilized. You don't have to derive the same thing. So our AR, if you recall, this is twice zeta omega n k divided by 1 minus k squared multiplied by 1 by R C. So A in this case shall be equal to twice zeta omega n k divided by 1 minus k squared. You also recall that R by L is twice zeta omega n, and 1 by LC equals to omega n squared. Therefore, this R and C can be replaced in terms of their equivalent values. R is twice zeta omega n times L, and C is 1 by omega n squared L. And you see jolly well that capital L and L cancel, omega n and omega n cancel, 2 zeta cancels with 2 zeta, and the expression becomes simplicity itself. It becomes k omega n squared, this omega n squared, divided by 1 minus k squared. This is the new value of k if the output is taken across the capacitor. Now let us proceed systematically to derive the numerical values of the other quantities that are wanted. Obviously, we require the value of zeta, we require the value of omega n, we require k, and that's about all. Then we shall be able to find everything else. Let us see. First thing is, we notice that by comparing the transfer function, by looking at the pole location, the real part is 4, minus 4 for all the poles, and therefore one conclusion that we get is zeta omega n should be equal to 4. Agreed? Then from the high Q approximation, loose coupling and high Q, we get omega n 1 plus k by 2, that is the upper pole in the upper plane, upper S plane, that is equal to 60, and omega n 1 minus k by 2, the lower pole in the upper half plane, is 50, and therefore omega n is therefore is equal to 55 radians per second. And by substituting this, you can get the value of k as
10 by 55.
that is 2 by 11. Agreed? 10 by 50. That is correct. Omega n and k. And if I know, so I know also zeta then. Zeta is 4 divided by 55. I don't require this value for calculating A, but zeta I should require for other calculations. So I can now calculate the value of A, the constant. A is k omega n squared divided by 1 minus k squared. So this is equal to 2 by 11 multiplied by 55 multiplied by 55 divided by 1 minus 4 by 121. And I felt lazy, I didn't calculate the whole thing, I just left it like this. There was no other cancellation. 550 into 121 divided by 117. 117, 3 is a factor, 9 is a factor, 13 is a factor, but none of them are factors of the numerator. So I left it at that. You have to use your calculator to get the values. Okay. Then I find out the maxima, the frequencies of maxima, that is omega 2m and omega 1m. I have already derived the values from that triangle. Okay, and the values are omega n multiplied by 1 plus minus square root of, this I did in the class yesterday, and also I took help of this in the example, but I did from the figure with numerical values. The general value is k square by 4 minus zeta square. This I derived yesterday. Okay, so if you substitute the values, my results come as 58 and 52. I didn't have to calculate the other one because symmetry. Say 55 plus 3, so 55 minus 3 is 52. So many radians per second, of course. The major deviation of working of this example shall come in calculating the value of the maxima. Okay, here h of j omega magnitude shall be a multiplied by the zero vectors drawn from the zeros, and there are 2 of them now, not 3. Therefore it would be m0 squared divided by all the 4, m1, m2, m3, m4. Agreed? Not cube, and therefore it will make a difference. Now obviously if omega is of the order of omega n, then m3 would be approximately equal to m4, would be approximately equal to twice m naught. Okay, the same as this. And therefore if we substitute this if I substitute this here, instead of putting omega n, this would be approximately equal to a divided by 4 m1 m2. All right. Also from that pole 0, from that pole diagram, okay, this is omega n, this is my picking circle, anyway, from the triangle, I have already done this derivation, so I don't know. Does the product m1 m2 change in terms of psi? It will remain the same because it's the same triangle that we are evaluating in 2 ways. One is in terms of its base and the height, and the other in terms of m1, m2 and the included angle. Therefore, let me not derive this again. M1, M2 M1, M2 is equal to omega n squared k zeta divided by sine psi. Was this the result derived earlier?
Yes, sir.
I guess so. Okay. Therefore, magnitude h of j omega, if you substitute, you shall get sine psi divided by 4 zeta 1 minus k squared. What is the difference? Difference is a factor of 2 zeta in the denominator. Previously it was sin psi by 2 1 minus k squared, now it is 4 zeta. Is that clear? What does this mean? That the maximum value here would be much higher than the maximum value in the previous case. Is that clear? Because of the occurrence of zeta. Psi is a very small quantity, it is increased by a factor of 2 but decreased maybe by a factor of 100, and therefore you will get much higher value. Okay. So the maximum value h j omega max would occur when psi is pi by 2, and therefore this is 1 by 4 zeta 1 minus k squared, and by substituting the values I get 55 multiplied by 121 divided by 16 into 117. It is not too high, it is about 3 times or 4 times at the most. Okay. The value is approximately 4, you can find that out.
But the zeta is also different.
Zeta is also different, of course. Okay, finally, the finding out the cutoff frequencies. Omega 2c minus omega n whole squared plus, if you recall that triangle, we have done this twice, plus omega n k by 2 minus zeta omega n whole squared, this triangle, if this is omega 2c, this triangle, okay, should be equal to what?
Root 2 into omega n k
Omega n k by 2 was the radius
into root 2.
squared. No, I am taking this square, so this multiplied by 2. Alright, from which we can find out omega 2c and omega 1c. The two roots of this is a quadratic
55 plus minus root 22.
plus minus, and therefore, pardon me,
55 plus minus root 22. 1 is plus.
55 plus minus root 24. 1 plus minus root 24. I don't know what that is. Well, my calculations, perhaps you are right. My calculations give omega 2c and omega 1c as 61 and 49. 61 and 49. I suspect this because root 24 is not a whole number. I did get a whole number, or perhaps I made approximations, I don't know. I have just noted the result, my rough calculations are elsewhere. Okay.
Not multiplied by 55.
It's not a whole product, it's simply 55 plus minus.
Oh, 55 plus, even then,
4 root 6 is approximately 6. No.
well, anyway,
5.
yeah, this is your base equation, okay, you can calculate that out. Now, that completes the example. Now, if I had taken the output across the inductor, could I have taken the output across the inductor?
Yes, sure.
Which means, hold it, there is a problem.
It will be across R and R.
Across the inductor. Could I take the output from here? Then, should I simply multiply I2 by SL? No, because there is a defect of mutual inductance also. The simpler thing would be, that's right. Your simpler thing would be take output as I2 R plus 1 over S, and then you calculate. And therefore, in the numerator, you would have an S cubed term and also an S squared term. You will have A1 S cubed plus A2 S squared divided by those quartic polynomial, alright, because of the 4 complex conjugate poles. Now, what can you say about this equation? Would it also be a band pass?
Yes, sir.
Yes, sir.
Sure.
Very big.
Surely it will be band pass.
Individually.
Is there a way I can get a high pass from here? Is there a way I can get a high pass from the double tuned circuit? You see, there are only 3 possibilities.
Inductor using it.
There are only 3 possibilities. I can take the output across resistance, I can take it across capacitance or I can take it across the secondary. And in all the three cases it is band pass. In all the three cases. Because the number of poles here is 4. You cannot create more than 3 zeros, and therefore there is no way that you can get a high pass response. You cannot get a low pass response either. There is no way that you can reduce the numerator to a constant, and therefore it is truly a band pass case. Now a small, yeah.
So why can't we create more than 3 zeros?
More than 3 zeros. Tell me how to.
So theoretically,
This is the degree of the, well, we have to enter into a bit of complicated discussion, but let me put this to you, that the number of energy storage elements that determines the number of poles in this circuit, and the number of zeros is determined by the way you take the output. Okay, the number of poles here is 4. It cannot be more than 4, because even without those approximations you have only 4 poles. Okay, and you cannot create more than 3 zeros because you have exhausted all the possibilities of taking output, and therefore there is no way you can introduce another pole here.
So what will be the equivalent A for this case? A1 S cube plus A2 S cube.
Oh, you have to find out A1 and A2. We have already found that out.
That
There is no equivalent A.
individual.
Now there are 2 A's. One is A1 and the other is
So
A2.
but each will give different frequency response because each individually is a double tune circuit.
Correct. You will have to find out the total frequency response from here.
So then it will be a superposition.
A combination, a superposition of the two. Yes, you can do the two, and then, but that doesn't give you the maximum and minimum frequencies. That investigation has to be done independently.
So how can
You find out your way. That's your problem, not mine. Okay. It's not difficult, I can assure you.
Same thing.
It's not difficult. You have to go a little bit deeper into it. Think about it, the solution will come out. Now, yesterday I had indicated to you that there are many ways of obtaining such responses, double tune, equivalent of double tune responses. I mentioned resistive coupling, I mentioned capacitive coupling. The other way could be that you take the output from a single tuned circuit, this is your input, and this output you apply through a buffer. Do you know what is a buffer? Buffer is an interface between two stages. The buffer virtually decouples. The buffer has two functions, one is coupling and the other is decoupling. The buffer decouples the response of the previous stage and the succeeding stage. In other words, these two stages are decoupled from each other. They work independently, which simply means that the input impedance here of the buffer must be very large compared to the output impedance here. Agreed? Then the buffer will not load the single tuned circuit. For example, if your single tuned circuit, you are taking the output across the capacitor, okay, and you connect anything here, you connect any other impedance here, that is going to affect the tuned circuit response. For example, if this is a resistance, if there is a resistance here, obviously if the single tuned circuit response was like this, with the resistance, well, this is what you expect. Usually it will become flatter, the Q shall be destroyed. Alright. So what we want is that this capacitance should not be loaded, and the way to ensure that is that if you see the Thevenin equivalent impedance of the single tuned circuit, this should be much less compared to the input impedance. In other words, the current after coming here should wholly flow through C. Very little current should flow through the connecting stage, through the next stage. Is that clear? And the usual thing to do is to use an op amp in the unity gain connection. If you know what is an op amp, this gives almost an infinite input impedance. Okay. Now, after the buffer, you connect this. Let me draw this diagram again. You have a single tuned circuit connected to a source, then you have a buffer, and you connect to another single tuned circuit. Take the output here. Now, this single tuned circuit, the two single tuned circuits may have slightly different resonance frequencies. They are close together, but slightly different resonance frequencies. Suppose one is this and the other is this. Then the overall response V0 by Vi, the magnitude, shall be the product of the two. Isn't that right? If the buffer has gain, let us say 1, unity gain, then the transfer function, let us say this is V1 and this is V0. So, this will also be V1, therefore, V0 by Vi shall be V0 by V1 multiplied by V1 by Vi, okay, which is equal to the product of the two, and therefore, the overall response may be somewhat like this. Which indeed looks like a double tuned response. Okay. So, you can couple, or you can combine two single tuned circuits without magnetic coupling or without resistive coupling, without capacitive coupling, to form a double tuned circuit response, to form a wide band selective response by simply doing this. You require an active stage, a buffer in between. Okay. Suppose, yeah.
So the last stage was also similar.
May not be. It is not similar because the resonance frequencies are different.
No, sir, the capacitor and resistor, if it took the output in a double tune circuit across the resistor and capacitor.
Okay, it will either be a low pass, high pass or band pass, but zeta should be much less compared to 1, so that even if it is low pass, even if it starts from 1, there is a high peak.
So, but if individual of both was at
Low pass,
yeah, double two maximum.
two maxima.
Dip in between.
No. This is a single tune circuit, it's not a double tune.
So in the last case, R plus 1 by C.
The previous one.
That is also single. Oh no, I am not talking of that at all. Alright. What I am talking about is two single tuned circuits being coupled and decoupled like this. They will produce a response which is similar to the response of a double tuned circuit. Alright, now what is your question? These are not double tuned circuits. If of both of them are double tuned circuits with slightly different tuned circuits,
Yes, that's right.
then I shall have a response like this. Let's say 1, 2 dips and so on, or maybe 4 maxima. I don't know. 3. Okay, there can be 4 maxima if they are slightly separated. Okay. Now, in general, I can couple many single tuned circuits like this. I can also couple 2 double tuned circuits or 3 double tuned circuits. Okay, and I can get a response like this. As many ripples as you want. Okay, if the ripples are equal, that is, if they fluctuate between same maxima and same minima, then obviously this is called an equal ripple response. Equal ripple response, or what goes in the literature by the name of Chebyshev response, Chebyshev, Chebyshev response. The name is derived from the name of the mathematician Chebyshev, who first gave a polynomial named after him, Chebyshev polynomials, which are equal ripple in nature. Okay, and this is why such filters are also called, such circuits are also called Chebyshev band pass filters. Mind you, Chebyshev is associated with equal ripple. Ripples should be equal. Okay. I can also design circuits in which there are no ripples. There is a flat pass band. By coupling several such circuits, I can so arrange that each is critically coupled, and the juxtaposition of the two is such that the fall due to one is taken care of by the rise due to other, and therefore I can get something like this. Such responses are called obviously flat responses. Okay? And one special kind of flat response is the so called maximally flat response, that is, at these frequencies as many differential coefficients of the function as possible vanish. We will come to such responses at the end of the course, but let it be known to you that maximally flat is associated with the name of an English mathematician by the name Butterworth. And these two kinds of responses are very popular to electrical engineers, that is Butterworth filters and Chebyshev filters, and I wanted to introduce to you right at this stage. Now, if a band pass filter of the type that we have been discussing is made by coupling two single tuned circuits whose resonance frequencies are slightly different from each other, then this arrangement goes in the literature by the name of stagger tuning. That is, the tuning of the circuits, individual circuits, are staggered. The resonance frequencies are staggered. Okay, omega 1, omega 2, omega 3, and so on. They are staggered one after another. This is called staggering, but close to each other. Okay. On the other hand, you can also get a circuit in which each tuned circuit is tuned to the same frequency. Let us say identical tuned circuits. Okay. Suppose this is the response of, let us say, one tuned circuit. 1. If I connect two such tuned circuits in cascade, exactly identical tuned circuits, same resonance frequency, well, what will be the response? Suppose the maximum is normalized to 1. I can always do that. Then you see the maximum does not change, but at any other frequency away from the maximum, 0.9 squared is 0.81, and therefore it becomes sharper. Okay. So, with two such circuits I shall get a sharper response, and if I connect another circuit now, I will get still sharper. So, this is a way of getting sharper selective responses or narrower bandwidths. You see, the bandwidth goes on decreasing, isn't that right? The bandwidth goes on decreasing, narrower bandwidth or sharper frequency responses, and such circuits are called synchronously tuned circuits. So, you know now the meanings of single tuned circuit, double tuned circuit, stagger tuned circuit, synchronously tuned circuit, resistively coupled circuit, inductively coupled circuit, capacitively coupled circuit, and so on.
In
Now,
in this case we can also get delta response.
delta response, delta in which domain? This is a frequency. This is the frequency response. Yes, you can get a delta omega in the frequency response. Is that what you are meaning? Not quite. Even if you couple infinite number of such circuits, you can't get a delta because of the same kind of problem that you have with Gibbs phenomenon. And we don't want it either. Who wants?
Once,
Who wants? If nobody wants, why should an engineer be interested? He should not make it like this. Okay.
Sir, if we were to normalize the
So
maximum,
increase 1.
then won't the maximum jump m square?
Well, I don't really care. You see, if the maximum is A0, it becomes A0 square. But what I wanted to show you is that of the resonance, the magnitude comes down. 0.9 square, suppose A0 was 50. 50 squared is 2500. 40 squared is 1600. The ratio of increase is much higher for the maximum than for the off resonance frequency. Okay, one interesting exercise that one can do at this point is to see how the selectivity increases. In other words, how do the bandwidths change, or how does Q of the circuit, Q of such a response is defined as the resonance frequency omega 0, if this is omega 0, divided by the bandwidth. Okay, and you can show that in a high Q tuned circuit, single tuned circuit, this Q is the same as 1 by 2 zeta. Alright, let me set for you two problems. One is to show that in a high Q single tuned circuit, if you define Q like this, it is the same as equal to 1 over 2 zeta. First question. Second question, if n number of such circuits are synchronously tuned and cascaded, that is, they are the same resonance frequency, identical tuned circuits, if they are cascaded together, what is the resulting Q? Would it increase or decrease? It would increase. I don't want to take a vote here. It would increase because bandwidth decreases obviously, so the Q must increase, and you can show that this is Q1 divided by, I am giving you the final result, it is your responsibility to show this, that this is 2 to the power 1 by n minus 1. Is that higher? Q1 is greater than Q1? Yes, yes. Q1 is the Q for a single tuned circuit. Okay? And Qn is the Q for n number of such tuned circuits put in cascade. The reason for this elaborate discussion is that these circuits are extremely useful at radio frequencies. They are also useful at frequencies higher than radio frequencies, but the way inductances and capacitances are used there are quite different. Okay? They are also used in integrated form. Capacitance in integrated form is no problem, but inductance is a problem. So, in integrated circuits, you see, inductance by definition, listen to me carefully. What is the definition of inductance? Phi upon
Number of
now I. Inductance is the flux per unit current. This is the definition of inductance, flux per unit current. And generation of a flux, a reasonable amount of flux. You see, if you want to make L high, then you should make the flux high. Okay? For the same current, you should make the flux high. Now, if the medium is not changed, that is, medium permeability remains the same. Medium permeability remains the same. For generating a large amount of flux, you require a large volume, which is not available in integrated circuits. Integrated circuits, the space is at a premium. All right. The other thing that you can do is to make mu high, that is the permeability high. Now, the highest permeability that is attainable is limited. You cannot make it infinite. And therefore, the value of inductance that you can obtain in an integrated circuit is typically of the order of picohenries, 10 to the minus 12, or even less, which are useless. And therefore, what one does in practice in integrated circuits is to simulate an inductor. Then let me give you this exercise. If you have a unity gain amplifier obtained by op amps, and you have two resistances R1, R2 at its input, and a capacitor comes from the output, then you can show that this impedance, input impedance, we have done 110, so you know how to analyze such circuits. You can show that this impedance is SC R1 R2 plus R1 plus R2. It behaves like a real world inductance with a resistance with it. So the Q is finite, it is not an ideal inductor. In theory, it is also possible to use op amps to make ideal inductors, but that we shall not discuss here, that will be the subject in some other course, I don't know. But whatever we do, however, in whatever way we produce an inductor, the basic principle remains the same. To produce a high selectivity, we shall have to simulate or actually use a physical single tune circuit. If we want a wide band, then we use stagger tuning or double tune circuits. If we want a narrower band, then obtained from a single resonance, then we use synchronous tuning. All right. These are the 3 points that you have to remember, and you cannot afford to forget for the rest of your life.